Hello everyone, this is our sixth tutorial. So let us solve few problems. Those are based on eigenvalues, eigenvectors, and characteristic polynomial, invariant subspaces. So those and some minimal polynomials. So those will occur. Let us look the first question. So here there is a linear transformation, linear operator. It is defined by t. T operates on the polynomial this, and it gives a0 plus a2x squared plus a4x to the power 4. Now we need to find if t is diagonalizable or not, the algebraic multiplicity of those eigenvalues. So let us solve this problem. Before first we will find the matrix representation of t. So from here it is clear t of 1 is same as 1 and tx is same as 0, because you can see if we put a1 equal to 1 and rest of the other things are 0, then it is simply 0. Similarly, t of x squared, it is simply x squared. Tx cube is 0. Tx to the power 4, this is actually 1. We get those things. Now if we write the matrix representation of t with respect to the ordered basis b, and let us b is same as 1x x squared x cube x to the power 4. So there are 5 entries. It will be 5 by 5 matrix, and we can see this is same as, so one can be, we can see that 1 can be written as 1 and rest of the other coefficients are 0. 0x to the power 4. So it is, if we write those things in column, then it is simply 1 0 0 0 0, and same thing for the second. It all those coefficients are 0, therefore the second column will be 0 0 0 0 0. Similarly, third column, only coefficient of x square is 1, so this is coefficient of 1, it is 0 x square, coefficient of x square is 1, rest of the other thing is 0. Third fourth row, fourth column, everything is 0 because it is already 0. And the fifth column, only coefficient of, sorry, I have made a mistake. It is x to the power 4, because you can see a to the a4 we have taken a4 equal to 1 and rest of the other coefficients are 0, so it is a4 x to the power 4. So coefficient of x to the power 4 will be 1 and rest of the other things are 0. So this is the matrix representation, and let A equal to this. A is defined to be this matrix. So first we will see, we need to find what are the eigenvalues of A. This is upper triangular matrix. Clearly eigenvalues will be diagonal, right? Maybe let us find the eigenvalues. So eigenvalues are determined by this polynomial det of A minus xi, and xi equal to 0. Okay. Instead of this, let us first find det of A minus xi, this determinant, and this is same as 1 minus x here. This is minus x, then 1 minus x, this is minus x, subtracting x from the diagonal, and rest of the other things are 0. So clearly 1 minus, this is 1 minus x occurring 3 times, So 1 minus x whole cube, and minus x occurring 2 times, so this is x square. And therefore characteristic, what is characteristic polynomial? Characteristic polynomial, this is simply x square. Just we need to take the positive sign of this, because characteristic polynomial is the opposite thing actually, that of xi minus a. So coefficient should be positive. That's why instead of 1 minus x cube, here we can see the coefficient of highest degree term is negative. So to make it positive, we just multiply with negative sign. So that of x minus I whole cube times x square. So this is the characteristic polynomial. Okay. So from here we obtain the characteristic polynomial, and now what are the eigenvalues? So eigenvalues or characteristic values, that is given by this equation, that of a minus xi equal to 0. But this imply x square into 1 minus x whole cube equal to 0. So that means x is either 0 or 1. So 0 will occur twice and 1 will occur thrice. So 0, 0, 1, 1, 1. So those are the eigenvalues. Now we can see that 1 occurs 3 times. So this is called algebraic multiplicity. Algebraic multiplicity of 1, this is 3, because it occurs 3 times. Okay, so this is correct. Now we can see characteristic, if we compare with this, it is clear that characteristic polynomial is their the root their coefficient their x cube occur, but we have seen that it should be x square times 1 x minus 1 whole cube. Okay, so this cannot be possible, so this is also false. Now we need to see if t is diagonalizable or not. So if we try to find the eigenvalues, we'll try to find eigenvectors. Okay, so eigenvectors with respect to 1. So again we have seen that this should be dat of a minus xi. So a minus xi will look like this matrix a minus xi. So here we put, so it is let v be an eigenvalue, then clearly a minus xi times v equal to 0. Here x equal to 1, we have assumed x equal to 1. Okay, so that is same as, so a minus I times v equal to 1, but we have already seen that a minus I, this will look like, here it will be 0, 0, 0, and those places is minus 1. So 0, then minus 1, 0, then minus 1, 0. So this is the from here it is clear that if we assume v equal to v is same as this vector v is same as x1 up to xn, here it is 4 by 4, so x1 up to x4, this thing, or maybe write v1 up to v1, v2, v3, v4. Then clearly we obtain v by solving this equation. equal to 0, but this will imply minus v2 equal to 0, and this row will give minus v3 equal to 0. So from here it is clear that uh, solution space of this equation, sorry, this is actually 0. Solution space of star is two-dimensional, right? Now we need to see, so those are the so eigenvector explicitly we can write eigenvector. So here we get those two relations. So it will look like v1, v2 and v3 are 0, but so sorry, it is v5. There are 5 vectors. It is 5 by 5 matrix. Okay, so we get those two relations. This is corresponding to second row and fourth row. So v2 and v4 are actually 0. So v1, then v2, then v3. v3 can be anything, v4 will be 0, and v5 can be anything. So those are actually eigenvectors. Okay, where vi can be any real number or any element from the field, given field. Okay, so this is actually v2, v4 equal to 0 and v4 equal to 0. So those are actually the eigenvectors. Actually, we don't need to find eigenvectors. It is enough to find what is the nullity of the what is the nullity with respect to those eigenvalues. Okay, that is rank of the eigenspace. We need to find this. So eigenvectors means those minus 0. 0 cannot be eigenvector, so we need to subtract. We need to remove 0 actually. Okay. So eigenvector with respect to 0. Eigenvector with respect to 0. So again, this is given by a times v equal to 0, because now x equal to 0. If we put x equal to 0, we get a times, this equation becomes a times v equal to 0. So we need to find solution space of this system, right? A was initially given 1, solution space of this system 1 0 1 0 1. So we need to find all such x1 up to x5. So clearly rank of A equal to 3. So nullity or rank of solution space which is same as nullity, whatever we said, this is actually 2, right? Because this is 5 by 5 matrix, it is simply 5 minus subtract the rank of the matrix. So rank of solution space, it is 2. So we already have, therefore we already have 5 linearly independent eigenvectors. Corresponding to 1, we have already found there are 3 linearly independent eigenvector, because rank of this thing is 2 and solution contain 3 linearly independent eigenvectors. So we can see that linearly independent, explicitly it will look like 0 0 0. It is spanned by those 3 things, 0 0 1 0 0 and 0 0 0 0. Fifth entry is 1. So it is spanned by those 3 things, but eigenvector, so we need to delete 0. So those actually this is called eigenspace. This is eigenspace because it contains all eigenvectors including 0. So this is called eigenspace. Okay. it is spanned by those three elements, and here we have seen that eigenvectors eigenspace corresponding to 0, it has 2 dimensions. Therefore we have 5. Before previously it was 3 plus extra 2, so we have 5 linearly independent eigenvectors with for A. Therefore, because for we already know the result for n by n matrix, if n by n matrix has n linearly independent eigenvectors, then it is diagonalizable. From this result, it is clear that this is diagonalizable. So that answer is also correct, that T is diagonalizable. Okay. So A and B are those are only correct answer, and C is also incorrect. Okay. So we'll see later why this is incorrect. Because today we'll not discuss minimal polynomials. Tomorrow we'll discuss. You can easily check why this is not incorrect. Just put if this is minimal polynomial, then T should satisfy this. Minimal polynomials means it is a polynomial. So suppose T satisfies this equation, and T is the lowest degree polynomial which satisfy some polynomial equation. So a polynomial equation, it will look like a to the power I, t to the power I, plus a to the power I minus 1, t to the power I minus 1, up to a to the power 0, t to the power 0, which is identity matrix. It is 0. So if this is 0 and I is the lowest possible degree, then this is called minimal polynomial. Lowest degree polynomial. Lowest degree polynomial. So if this is the lowest degree polynomial such that this annihilates T, then this is called annihilating. This is called minimal polynomial because it is lowest degree. So you can check here that if you put T and T minus 1 whole square, this is actually not 0. So let us verify this. This is not so difficult. So we have seen that so actually uh, instead of matrix, let us try with the equation actually. T of a0 plus a1x plus a2x square a3x cube plus a4x to the power 4. This will give us a0 a2 a4, right? So a0, this is same as a0 plus a2x square plus a4 x to the power 5, sorry, a4x to the power 4. That was our initial T. Yes. Now if we apply, so the equation was x into x minus 1 whole square. So this should satisfy if T is minimal. But let us see if this is satisfying or not. So okay. So what is T minus identity? T minus identity acting on this polynomial, so denote it by P. So T minus identity acting on this polynomial P, it is simply It is simply this minus ix. So it is t on p minus identity on p, which is p. So we'll get, if we subtract uh, first polynomial from this polynomial, then it is clear that only odd term will survive, minus a1x minus a3x cube. Okay. Now again we apply t minus I. So t minus I whole square p. This is same as t minus I acting on t minus ip. I means the identity operator on this vector space. So okay, but this is t minus ip is already there. So this is actually t minus I acting on minus a1x minus a3x cube. But there are only odd terms. So t, if we apply t, it will be 0, because that by the this rule, just put t on this thing. Okay. So this is t minus t applied on this give us 0, minus identity applied on this thing, it will be negative, so it is plus a1x plus a3x cube. And now t, again we apply t on this thing, t applied on t minus I whole square p. This is same as t applied on a1x plus a3x cube. So this is 0, right? But though t satisfy this equation, x minus x times x minus 1 whole square equal to 0, but we can see that t into t minus I, this is also 0. From here it is easy to see, right? Just apply t on this thing, take any polynomial and apply t, then from here it is clear this is 0. So the lowest degree polynomial, therefore the minimal polynomial, this is same as t times t minus, sorry, instead of t we write x, minimal polynomial. So if we denote it by m, minimal polynomial of x, this is same as x times x minus 1. Okay. So from here it is clear the minimal polynomial of this thing is x times x minus 1. And this result, you can there is a result, let me write it. So if a is diagonalizable, then minimal polynomial of a equal to product of x minus lambda I, where lambda I are distinct, lambda i's are distinct eigenvalues. So here we have already seen that it is actually diagonalizable, and the only distinct eigenvalues in this case is 1 and 0. Those are only two distinct eigenvalues. Though they have multiplicities, but those are different eigenvalues. So, for this example, or for question number 1, minimal polynomial of a, this is same as x minus 0, 1 eigenvalue, and x minus 1. So you can compare this with this, right? Those are same. So this is very useful result. If you don't know the result, then it will be, you need to do those kind of works, which is time consuming. Okay, let us solve this question. So T be a linear operator on F3. Let the matrix representation T of T with respect to the standard basis on F3. This is same as this. Then which of the following statement are correct? Statements is okay. Only a single correct. So let us solve. Again we denote it by A. Then we need to find what is date of A minus xi. So it is simply just subtract from the diagonal, and remaining things are same. But this determinant is same as 1 minus x times minus x into minus 1 minus x minus 2. Okay, but this is same as 1 minus 6 times x squared plus x minus 2. But from here it is, again we can factorize, because plus 1 can be written as 2 minus 1. Okay, plus 1. So from here we can factorize it by 1 minus x plus 2 into x minus 1. So we know that by Cayley-Hamilton equation, by Cayley-Hamilton's theorem, the operator T satisfies its its characteristic polynomial characteristic equation. So here we can see characteristic equation chi x. This is same as chi x equal to 0, we write in this. So here chi x is same as this thing. So it is 1 minus x times x plus 2 into x minus 1. So this is the characteristic polynomial. So T will satisfy this equation. So instead of where there is x, we will put T. So we have I minus T times T plus 2 I. Wherever there is some scalar, we just replace it by identity or I. Okay, so T minus 1. So there is scalar, so we replace it by I. So this is the T will satisfy this equation, right? But if we explicitly write, then again this is already actually given. So this is actually T square plus T minus 2, and this side is I minus T. So this is same as this, but this is same as, just multiply. So just take a negative sign, so that this become plus T and this become minus I. So this is T cube, then minus T square plus T square, it is cancelled, it gets cancelled. Then minus 2T and minus T, which is minus 3T, and plus 2. So this should be the correct answer. T cube minus 3T plus 2I. There is identity. I should write I. So T cube minus 3T plus 2 identity. So this is correct. but we need to see other options are false. So from here it is clear that eigenvalues eigenvalues are x equal to 1 minus 2 and plus 1. Okay, so those are the only eigenvalues. But if we put plus 1 here, you can see this is plus 1. So you replace t by 1. So if we just put 1 in the place of t, it becomes 1 minus 2 plus 3 minus 2. So this is 4 4, so this is 0. But if we replace with by, there is just write t equal to 0, t equal to minus 2, replace it with minus 2, then we get minus 2 cube minus 2 times minus 2 whole square plus 3 times minus 2 3 times minus 2 minus 2, which is same as minus 8, then minus 8, then minus 6 minus 2. So this is non-zero. So from here it is clear that this factor t plus 2, this factor does not occur. This does not divide this thing. So this cannot be eigenvalues because all those factors should occur. At least those two things should occur, t minus I and t plus 2i. Okay, so it should be all those things which satisfy, that is all those annihilating polynomial, it at least contain those product of distinct product corresponding to the distinct eigenvalues. So for eigenvalue minus 2 we have this factor, for eigenvalue plus 1 we have this factor, and this also repeated, these two are repeating, but at least those two different things should contain. But here we can see t plus 2 does not divide this thing, so this cannot be, cannot annihilate the transformation. Now here for this we just put replace t by plus 1. Again we can see that it is 1 plus 2 minus 3 plus 2. So this is 5 minus 3, which is 2, not equal to 0. So this is also false. Okay. And here if we put t equal to 1, it is 1 plus 3 plus 2, which is 5, non-zero. So this is also non-zero, so this is also false. So those are actually false. Okay, so next question number 3. Here is 4 by 4 real matrix, and it is given by this equation. Then which of the following statements are correct? Okay, we need to find characteristic polynomial. Same technique. Here you can see that it is, if we just put a block, then it is some kind of block matrix, block matrix, but it is lower triangular because that upper thing contains 0. If we put into a block form, then this is 0 and this is some b and c, and for those kind of thing determinant is actually easier. So determinant of this thing is same as determinant of a times determinant of c minus det b times 0, which is 0. So this is the correct determinant. Okay, so for those kind of block, calculating determinant is easier. Now we need to calculate this thing, determinant of a minus xi. So it is just subtracting from the diagonal minus 1 minus x, 2, 2, 1, and this is 0, and 1 minus x, 2, 0, minus x, and minus 2 other things are same. So this is actually 0, 0 matrix, 2 by 2 0 matrix. Okay. Now determinant of this thing is same as 1 minus x, 2, 2, 1 times 1 minus x, 2, 0 minus x. Okay. Now this is same as 1 minus x times 1 minus 4. So this is minus 3 minus x. If we take minus common, then it is 3 plus x. Then there is minus x times 1 minus x, this determinant. So if we just therefore characteristic polynomial chi x, we denote characteristic polynomial by chi. Okay, so this is same as just we need to produce a polynomial whose highest degree term should be plus 1. So we need to multiply with negative sign so that it becomes x plus 3. 3 plus x is the same as x plus 3, and then it is x, then multiplying with negative sign it will be x minus 1. So this is the chi x, because we know chi x is same as det of x a minus a. So that's why some negative sign, we need to multiply with some negative sign. So this is the characteristic polynomial. From here it is okay. So I have done some mistake. Is it? Oh, this should be 1 minus x. We have not subtracted. So this is 1 minus x, because degree should be 4. It is 4 by 4 matrix. So those kind of thing you should note. Otherwise there will be mistake. So this is same as 1 minus x whole square minus 4. That is, we can simply calculate x square 1 minus x whole square, x square minus 2x plus 1 minus 4, that is minus 3. Now minus 2 can be written as minus 3 plus 1. That's why we have factorization x minus 3 and x plus 1. So this is x into x minus 1. Okay, so this should be some. So this is chi x. Okay. So chi x, from here it is clear that chi x, it will look like x times x minus 3 times x plus 1 times x minus 1, and it is certainly it is not same as this. So characteristic polynomial is not this, and this is also not true. Those are not characteristic polynomial. Now a is not diagonalizable. From here we can see that all eigenvalues are distinct. So what are eigenvalues? Eigenvalues are, from here it can be seen that 3 is eigenvalues plus 1, so we have minus 1, because what are the eigenvalues? Eigenvalues obtained by equating 0, right? So if we equate 0, then we have a solution x equal to, from here x equal to plus 3, from here x equal to minus 1, and x equal to 0, x equal to plus 1. So those are the solution. So those will be the eigenvalues. 0 and plus 1. So all eigenvalues are distinct. If this kind of situation occurs, then it is diagonalizable, because corresponding to distinct eigenvalues we have linearly independent eigenvectors. So there are 4 eigenvalues different. So we have 4 linearly independent eigenvectors. 4 linearly independent eigenvectors. So 4 linearly independent eigenvectors means it is diagonalizable, because it is already 4 by 4 matrix. So it is diagonalizable. So that option is also incorrect, because A is diagonalizable. Now what is the geometric multiplicity of 1? Clearly all eigenvalues are distinct. Now geometric multiplicity cannot be more than 1. So before that, let us see what is geometric multiplicity. Okay. So let lambda be an eigenvalue of A. Then we know that algebraic multiplicity this is number of times an eigenvalue occurs by solving characteristic equation. For example, suppose x minus 1 whole cube times x square is characteristic polynomial. Then from here, if we solve chi x equal to 0, solving this, we have x equal to 1, it will occur 3 times. And x equal to 0, x square equal to 0 means x equal to 0, it will occur 2 times. So algebraic multiplicity of 1, this is 3, and algebraic multiplicity of 0, this is 2. Okay. Now, what is geometric multiplicity? It is actually dimension of eigenspace corresponding to the eigenvector. Okay. So for example, in previous example, here we have seen that corresponding to 0, the dimension of eigenspace, it is yes, so dimension of eigenspace is 2. So 0, the geometric multiplicity of 0, it is 2. And for this example, dimension of eigenspace corresponding to 1, it was actually 3. So geometric multiplicity of eigenspace is 3 in this case. Okay. So this is only true for diagonalizable. In diagonalizable case, geometric multiplicity and algebraic multiplicity, those are same. So if those two things are same, then that is diagonalizable. Earlier we have seen that matrix was diagonalizable. So this is geometric multiplication. I write 2 results. One result is geometric multiplicity of eigenvalue lambda is always less equal to algebraic multiplicity. Okay, and another thing, equality holds for all eigenvalues, then so this is if and only if A is diagonalizable. Okay, so those are some important results. Here you can see that geometric multiplicity of 1, so it is always less equal to algebraic multiplicity. So 1 occurring here 1 times, so algebraic multiplicity of 1 is 1. So algebraic multiplicity of 1, this is actually 1. So geometric multiplicity is also 1. And geometric multiplicity will be always at least 1, because we always have eigenvectors corresponding to any eigenvalue. So this is true, that geometric multiplicity, it is actually 1. Okay, let us solve next question. Question number 3 is, so here question number 4. Here you can see that A is 4 by 4 matrix, and the characteristic polynomial and minimal. Okay, we need to see if characteristic polynomial and minimal polynomial, those two are same or not, and other things. Okay, so again, A is a block matrix. If we write in a block, then it is easier to see, easier to find determinant and all those things. So first we will calculate determinant of A minus xi. So it is same as minus 1. Similar to the previous calculation, we have minus 1 minus x, 1 minus x, 2 2. This is unchanged, and for the last thing we have 1 minus x, 0 minus x means minus x, and 2 minus 1. So now this is same as okay, x minus 1 times x plus 1, which is x square minus 1, and minus 4, that is x square minus 5, right? Okay, and the second thing will be minus x times x, so minus x times 1 minus x plus 2, and we have already calculated this thing, minus x times 1 minus x plus 2. Oh no, that is different, so we need to calculate it again. So if we write here this thing, so that is actually x square minus x plus 2. So again, if we factorize, this will become no, there is positive sign, so it is not easy to factorize. But if we put it equal, if we write this equal to 0, then this equation solution will be x equal to plus 1 plus minus root over b square minus 4ac. So b square means it is 1 minus 4ac. 4ac means 2. So minus 8 by 2. So which is same as 1 plus minus root 7i by 2. So those are actually the solution. Therefore, characteristic polynomial. So from here it is clear that x square minus x plus 2, this can be written as x minus, so if x minus that 1 plus root 7I by 2 times x plus 1 plus root 7I by 2. Okay, so from here it is clear that what are the what are the eigenvalues. Therefore, eigenvalues. So what are the eigenvalues? From x square minus 5 equal to 0, if we solve here, we will get x equal to plus minus root 5. Okay, x equal to plus minus root 5. And we already have from here, it is 1 plus minus root 7I by 2. So those are 4 eigenvalues, and 4 eigenvalues are distinct. So whenever the eigenvalues are distinct, characteristic and minimal polynomial are same, because any annihilating polynomial take at least it should have at least one factor corresponding to eigenvalues. For example, let us write explicitly the result. So if chi x, it is looking like some, instead of product, let us write x minus lambda 1 times some n1, x minus lambda 2 times n2, up to x minus lambda n times maybe lambda k times nk. Then minimal polynomial, then x minus lambda 1, all those factors, x minus lambda 2 up to x minus lambda k, all those factors at least occur one times in minimal polynomial. So all those factor divides minimal polynomial. From here it is clear that if all those eigenvalues are distinct, right, there are 4 distinct eigenvalues, then characteristic and minimal polynomial, those two will be same, because minimal polynomial, all those factors will occur at least one times, but occurring at least one times will give the same polynomial, right, same polynomial as here. But minimal means its degree should be always less equal to degree of this, so that is the minimal possible. That's why characteristic polynomial and minimal polynomial, those two are same in this case, because of distinct eigenvalues. All eigenvalues are distinct, all those 4 eigenvalues. Now sum of complex eigenvalues minus sum of real eigenvalues. Okay, let us calculate. So sum of complex eigenvalues minus sum of real eigenvalues. So we have already seen that plus, okay, 1 plus minus root 7 by 2i. So 1 plus root 7 by 2 plus 1 minus root 7 I by 2 minus sum of real eigenvalues. So real eigenvalues are plus root 5 minus root 5. So root 5 minus root 5. So this is 0 and this is 1, because plus root 7 minus root 7 will get cancelled. So this is true actually. So this option is also true. Now determinant of A is 10. Is it true? Determinant of A is 10. Okay, let us see what is the product of eigenvalues. Instead of finding product from here, it is more easier to see. Just put x equal to 0. Putting x equal to 0, we have determinant of A minus 0, which is determinant of A. This is same as put 0 here. Okay, so this is -5, and putting 0 here we get times +2, which is -10. So determinant is -10. So this is false because there is issue with a sign. Those are eigenvalues of 2i minus a. So we have already seen if a has some eigenvalue lambda, then this result is also important. If a has eigenvalue lambda, then polynomial a, this has the same eigenvalue as the eigenvalue p lambda, polynomial of lambda. So in this case, in this question the polynomial, so polynomial here pa, the polynomial is in this question, the polynomial pa is same as a minus I. So the eigenvalue will be lambda minus 1 because we treat I as +1. Okay, so eigenvalues will be lambda minus 1. We need to find complex, those are complex. So 2i minus a, here the polynomial is 2i minus a, 2i minus a. So 2 minus lambda, 2 times 1 minus lambda. Minus lambda means here we have seen that eigenvalues are those type of thing, 1 plus minus √7 by 2. If we subtract, this will becomes 3 by 2 plus minus √7. So this is actually false. This is also false. So those are only correct. A and B are the only correct answers. Now question number 5. Okay, here T and U, two linear operator on V, which satisfies the commutativity Tu equal to Ut. Nt, Nu denotes null space of Tu respectively. Rt, Ru denotes range space. Then which of the following is true? First one is Nu is not invariant under T. Is it true? Let us verify. So let x belongs to Nu. Sorry. X belongs to Nu. This will imply null space, means U times x, U operating on x will give you 0. Right? Then the question is, okay, so what is invariant means? So a subspace W containing V is said to be T invariant if T on W, this contains in W. Okay, this is the difference, and this is the definition of T invariant subspace. So now we need to see if x is okay. Nu is not T invariant. So null space of U is not T invariant. x belongs to nu. Now we need to see that t applied on x, if this belongs to nu or not. So if we apply u here, this will give you by star, this is same as tux by star, but we already have ux equal to 0, which is 0 by 1, right? So from here the implication is tx belongs to nu, right? Tx also belongs to null space of u. That is so we have taken an element and we have applied t over this element, and this also belongs to that, that is t applied on nu, this contain in nu. So from here it is clear that this is actually nu is t invariant, so this is false. Now ru is not invariant under t. So again let us see if ru is t invariant or not. So let x belongs to ru. X belongs to ru. So what is a typical element of ru range space? So it will look like, x will look like uh, um, u times some y, right? Now if we apply t, so apply t, so this will imply tx equal to, then this is x equal to uy for some y belongs to vector space v, right? Now this is tx, this is same as tuy, but tu is same as ut, so this is uty. So tx belongs to, this belongs to range of t, right? Range of u, range of u. What is the question? Ru is okay. We have taken an element from ru and we get ru is t invariant. So this belongs to range of. Therefore, we obtain t applied on ru, this contained in ru. Right? Range of u is actually ru. This is the notation here. So from here, the implication is ru is t invariant. Invariant. So this is also false. Both are t invariant. Nt plus ru is invariant under t. Nt plus ru. Let us again apply t on nt plus ru. Okay. So in an element of nt plus ru, it will look like x plus some another y, or just apply t on this subspace. Let us apply t on nt plus ru. Okay. So if we apply t over null space of t, it will cancel that those part, right? So it is same as t applied on ru, but we have already seen that t applied on ru contain in ru, but ru also contain in t. We have added something nt plus ru. right? From here it is clear that NT plus RU is T invariant. So this is true. Now RT and NT are U invariant. Is it true or not? RT plus NT. Okay. So NU is T invariant. So by the same method, because just change the role of U and T. From here, we have already seen that from here we obtain that NU is T invariant. Similarly, from here, just exchange the role of T and U. We will have NT is U invariant. And from here, similarly, uh, RT range T is U invariant. Okay, so RT and NT both are U invariant. This is true, right? So C, D, those are correct answers for question number 5. Is it okay? Everything. Yes, C, D are correct. Okay. Now this question here, we need to see that if those matrices are diagonalizable or not. Okay, let me write the solution. So from here, what are the eigenvalues? We can see that again we just use that result. This is not a result, it is just a observation. What was that observation? That upper triangular or lower or upper triangular matrix eigenvalues of those kind of matrix are the diagonal entries. So we need to check if the geometric multiplicity and algebraic multiplicity are same for all those ABCD options. If geometric and algebraic multiplicities corresponding to every eigenvalues are same, then this will be diagonalizable. Otherwise, not. Okay. So for first option, if we look at first option, here eigenvalues, we can see diagonal entries are 1, 2, 1. So eigenvalues are 1, 2, 1. So algebraic multiplicity of 1, this is actually 2. And algebraic multiplicity of 2 is 1. So we don't need to worry about 2 because here algebraic multiplicity is 1. So only problem which may occur, it is for when algebraic multiplicity is greater than 1. So that is the problematic part. So we need to find eigenvectors corresponding to 1. So if we just subtract denoted by A, then A minus xi, this will look like this matrix 0, 1, 0, 0, 1, 0, 0, 0, 0. So rank is 1. Rank of this matrix is 1. Therefore nullity or solution space, rank of solution space, this is 2. So solution space has rank 2. Therefore geometric multiplicity for x equal to 1. We are looking at this. Yes. Multiplicity of eigenvalue 1. This is same as nullity or whatever we call rank of solution space of A minus I, and this is also same as the rank of, that is dimension of, this is actually same as dimension of, just alternatively we can see dimension of eigenspace corresponding to 1, so here it is same as 2, right? Of x equal to 1, this is actually 2, nullity is 2. That's why we have geometric multiplicity is 2. So algebraic multiplicity of 1 was already 2, but this is same as geometric multiplicity of 1. Therefore algebraic and geometric multiplicity are 2. Therefore this is actually diagonalizable. Okay, so the conclusion is A is diagonalizable. Now let us look at B, this matrix. So for B it was okay. Now for B, here eigenvalues, those are 2, 2, 3, those are the diagonal entries. Now again 2 may create problem, so because algebraic multiplicity of 2 is greater than 1, so algebraic multiplicity of 2, this is 2, it occurs 2 times. Now if we subtract A minus 2i, this will becomes 0, 0, 1, 1, 0. Sorry, not A, here we have denoted by B. So 0, 0, 0 and 1. But we can see that rank is 2, rank equal to 2. Therefore nullity, or just we have already seen that is called eigenspace. Okay, so dimension of eigenspace will be, this is 3 by 3 matrix, so it is 3 minus this rank, 3 minus 2, which is 1, that is the nullity. So clearly geometric multiplicity, we get geometric multiplicity of 2, this is 1, which is less than algebraic multiplicity, right? So it is not diagonalizable. The conclusion is B is not diagonalizable. Next option is, we need to check if C is correct or not. Let us write C. Here again eigenvalues are 1, 1, 2, 1 occurring twice, so we again denote it by C, C minus I, C minus 1 times I. This is what we need to check. This is 0, 0, 1, 1, 0, 0, and rest of the things are 0. So this is the upper triangular matrix. Again, rank 2, nullity 1, rank 2, nullity 1. Nullity 1 means Therefore, geometric multiplicity of 1, it is less than algebraic multiplicity, because algebraic multiplicity it occurs twice. So this is less than, strictly less than 2. So those are not same. Hence, this is not diagonalizable. Option D. For D, again we just same process. Subtract, eigenvalues are 1, 2, 2. So the problem may created by 2. So again D minus 2i. If we write D minus 2i, it will be the lower triangular matrix minus 1, 0, 0, and then minus 1, plus 1, 0, and above entries are 0. This is the lower triangular matrix. From here you can see that is, those are zeros. Okay, so from here again rank is 2, therefore nullity 1, which is nullity 1 means it is geometric multiplicity of 1, geometric multiplicity of 2, that is it is for geometric multiplicity of 2, because this is D minus 2i. Geometric multiplicity of 2, it is nullity is actually 1, but this is same as geometric multiplicity, which is strictly less than algebraic multiplicity, because algebraic multiplicity of 2 is 2, right? So again, equality, there is no inequality, there is strict inequality, so D is also false. Only A is the correct answer. So that is question number 7, right? Question number 6. 7 and 8 are similar. Okay. Okay, that is question number 9. Let us see what is this question. NB denotes null space. B times x equal to 0. All those x belongs to Rn. That is solution space or null space, whatever we say. And then dimension of null space of A minus 3i equal to 2, A minus 5i equal to 1, rank of A equal to 3. So first let us look at what is the meaning of rank of A equal to 3. Rank of A equal to 3, this means solution space of A, its dimension will be dimension of the solution space. It is, that is nullity. It is simply this is 4 by 4 matrix, so 4 minus this rank, 4 minus 3, which is 1. Okay, so dimension will be 1. Now dimension of dimension of this null space A minus 3i, this is 2, right? Therefore we have, alternatively we can see this is actually same, this is same as this null space of A minus 3i, that will give eigen space with respect to, so let me write null space of A minus some xi or A minus lambda I, this is actually the eigenspace corresponding to lambda, right? So what is the dimension of the eigenspace? This is same as dimension of the eigenspace, therefore dimension of this eigenspace, this is actually geometric multiplicity of lambda. So from here it is clear that here dimension is 2, so geometric multiplicity of lambda equal to 3 is 2. So x minus 3 whole square will occur in the characteristic polynomial. Similarly, x minus 5 to the power 1, this will occur in characteristic polynomial. And here geometric multiplicity of corresponding to 0, solution space of A, that is it is same as nullity of A, right? Nullity of A is same as nullity of A minus 0i. So there is another factor x minus 0. Now this is 4 by 4 corresponding to 4 by, so this will divide those factor will occur in characteristic polynomial. Polynomial, but it is 4 by 4 matrix, right? Since A is 4 by 4 matrix, this is the characteristic polynomial. So okay, since A is 4 by 4 matrix, so therefore if we denote it by px is the characteristic polynomial, right? So this is the actual characteristic polynomial, and from here it is clear that eigenvalues are 3. That is, if we equate px equal to 0, then we'll get the solution will be 3, 5 and 0, right? So 3, 5, 0 are the all eigenvalues. This is correct. And what about determinant? Since null space of A, dimension of null space of A equal to 1, so determinant is 0. Otherwise, just multiply 0, 3, 5. Product of eigenvalues, that will be the determinant, which is 0. A is not diagonalizable. Can we conclude if it is diagonalizable or not? No, it can be diagonalizable or it cannot be. Whatever, there are two possibilities. For example, if we take A to be let A equal to this thing, because it may happen that geometric multiplicity of 3, this is less than algebraic multiplicity. One example will be like this. So suppose this diagonal block diagonal forms. So 3, 3, there is diagonal and there is some 1, and other entries are 5 and 0 is another eigenvalues, and rest of the other things are 0. From here we can easily see that this cannot be diagonalizable, because if we just subtract 3, it will create a problem, right? If we subtract 3, it is similar to the previous examples, these examples, right? It cannot be diagonalizable, so this is false. Trace of A is 11. So what are the sum of eigenvalues? So sum of eigenvalues, it is, note, we need to take that is algebraic multiplicity of 3 is 2, so we need to add 3 two times, otherwise it is not sum. Plus 5 plus 0. So this is 11. So that is also correct. Because trace is same as sum of eigenvalues. So those are correct answers. Now question number 10. Here the first question is a square is 0. Now can I conclude if a is diagonalizable over complex numbers? So take this example. Again, the problem will occur because of algebraic multiplicity may not be same as geometric multiplicity corresponding to those eigenvectors. That is the problem. That is the obstruction behind diagonalizability. Now before that, let me mention a fact. If A satisfies a polynomial equation, then eigenvalues of A will also satisfy the same equation. For example, here the polynomial equation a square equal to 0. Let us see why this is true. So let lambda be an eigenvalue of A. Eigenvalue of A. Then a square equal to 0. This will imply a square times. So lambda be an eigenvalue of A and V be an eigenvector corresponding to lambda. Then a square V, this is also 0, just multiply with V. But a square V means it is A times AV equal to 0. So again AV equal to same as lambda V. So A times lambda V equal to 0. But again, just take lambda common, then we'll have lambda times AV equal to 0. But this is same as AV is same as lambda V, so we have lambda square V equal to 0. But eigenvalues are non-zero. Since V is non-zero, we get this will imply V lambda square equal to 0. So similarly, you can see that if something's if A satisfies some polynomial equation, then eigenvalue will satisfy also the same equation. For example, A square equal to 0, and we get lambda square equal to 0. The eigenvalue will satisfy the same equation. So from here it is clear that for option A, eigenvalues are lambda equal to 0. 0 are the only eigenvalues. So 0 is the only eigenvalue of A. So we need to construct a counter example if this is false. So take this example. For example, instead of n by n matrix, let us consider this 2 by 2 matrix, 0, 1, 0, 0. Here you can see that 0 is the eigenvalue of this matrix. So if we write A equal to this, then A square, what is A square? It is 0, 1, 0, 0 times 0, 1, 0, 0. But this is same as 0, 0, 0, 0. A square equal to 0. So though but the problem is A is not diagonalizable, because you can see that geometric multiplicity of 0, this is actually equal to 1, right? Because rank of A equal to 1, therefore nullity of A equal to again 1, 2 minus 1, which is 1. So geometric multiplicity of 0 is 1, which is less than 2, which is the algebraic multiplicity of 0. 0 will occur twice here. So geometric multiplicity of 0 less than algebraic multiplicity of 0. So this is not diagonalizable. So we have successfully constructed a counter example which shows us that A satisfies this equation, but A is not diagonalizable. Now the second thing is A squared equal to I, then A is diagonalizable over real. So we'll look it later. First, A squared equal to A, then A is diagonalizable over complex. So for here, counter example will be like this. Counter example, take A equal to identity, which is automatically diagonalizable because identity itself is diagonal matrix. So this is diagonalizable and it satisfies the relation A square equal to A, right? But identity is already diagonal. That is, it is also diagonalizable over real. Okay, so that option is wrong. But A is diagonalizable over R. So that is the problematic part. Only over complex. This is false. It can be diagonalizable over R as well. So this is also false. Now the option D, A minus 2I, A plus I, this is 0. Then A may be similar to, so let me copy this thing. So A minus 2I, this is 0, then A may be similar to a diagonal matrix. It is not necessarily. For example, we need to again construct a counter example for this. So okay. So from here it is clear that eigenvalues of A, if lambda be an eigenvalue, then lambda will satisfy the same equation, lambda minus 2 into lambda plus 1 whole square equal to 0. So this is equal to 0, but this will imply that lambda eigenvalues are 2 and minus 1. Those are the only eigenvalues. Now we need to construct a matrix which satisfies this relation, but it is not diagonalizable. So again, 2 occur one time, so it is okay. But for minus 1, we can write it as minus 1, 0, minus 1, 1, 0, 0. Will it satisfy the equation? This is the question. So if we square this thing, eigenvalues are minus 1. Okay, so again we can easily see that this equation is satisfied by this matrix. So why this is true? Because a minus 2i, this is 0, that is a minus 2i times a plus I whole square. Let us check if it is 0 or not. This will become 0, and the same thing, minus 1 1 0 minus 1, this block matrix, and a plus I whole square, this is same as 3, and now sorry, minus 2, we need to subtract minus 2, so this is minus 3, and this is also minus 3, so this is 3, and the rest of the thing, what are the rest of the things? So adding plus 1 to the diagonal, so this is 0 1 0 0. Now if we take the square, then this is clearly, the first one is same, 0 minus 3 1 0 minus 3, but the second thing here, it is 9, and okay, 9, and this block is 0 0 again, and this block is second column, so this is also 0. So if we multiply this is the 0 vector, right, 0 matrix. So this is also false, because we have successfully found a matrix A which satisfies this relation, but this cannot be diagonalizable. Why this is not diagonalizable? Because again, geometric multiplicity of minus 1, this will be less than 2. This is strictly less than 2. This will be 1, because rank of this block, this is, if you subtract, that is if we add plus 1, then rank of this block will be plus 1, right? So that is the problematic part. So D is also false. Now if a square equal to a, then a is diagonalizable over complex number. Okay, let us check for the option C. Given a square equal to a, this will imply eigenvalues lambda square will satisfy the same equation. Lambda, is it a square? Oh sorry, we have not checked option B. C is already done. C is also false, right? A is checked, C is also false, D is false. Now option B, a square equal to I. So lambda square equal to 1. From here it is clear, lambda will be plus minus 1. Now, so let us solve. Okay, here we should use, we need to use Jordan canonical form. So it says P inverse AP for given any matrix A, there exists some P invertible matrix such that P inverse AP, this will be a block matrix. Okay, some block diagonal matrix. It will consist some blocks. That is only block. There will be some block entries. So except those things, everything's are 0. Those will be the only non-zero block. And those non-zero block, those will this kind of blocks, it will look like diagonal, but above the diagonal there can be some non-zero entries. For example, here or here, those are the possible non-zero entries, right? So now given lambda is 1, so all those diagonal entries should be 1. So we have already written 1. So those are usually lambdas, eigenvalues, repeating eigenvalues. Now here all those, so P inverse AP, it should look like some 1 1 1 everywhere 1, and there are some blocks, right? But if except the diagonal, if there is some, suppose one occur any other place except the diagonal entry, diagonal place, then clearly that a square will not satisfy the relation. A square will not be identity. If the one, if so, if one occurs any place other than diagonal entries in J. This is called Jordan form. So it is not three. There can be other blocks also, more than three blocks. Okay. So if one occurs other blocks, other entries, other one occurs non-diagonal position, then a square cannot be a, right? Because those are zero. Those are actually zeros. So if one occurs uh, any place other than diagonal, then a square cannot be identity. This is easy to verify. For example, let us check with this example. So this is 1 1, and suppose 1 occur in this place, then just multiply, a square cannot be identity. Sorry, just multiply those two things. This is 1 0, but this is 2 1. That is the problem. It cannot be same as identity. So this is actually true. Only identity is the possible Jordan form. So if P inverse AP is identity, therefore P inverse AP must be identity, because otherwise a square not equal to y. That is the problem. Then a square is not equal to y. Therefore P inverse AP must be identity. This is must. Otherwise this relation will not be satisfied. So P inverse AP is identity. Just multiply with P and P inverse on the left and right. This will give P inverse P inverse, which is I. So A must be identity. So this is true. A is diagonal. Sorry, I have done a mistake. So plus minus 1 also can occur. Okay. So it is not completely identity, but P inverse AP, it will look like some, that is some diagonal matrix, plus minus 1, plus minus 1, plus minus 1. Okay. Some diagonal matrix which contains plus minus 1. So if we multiply this thing with uh, P and P inverse, this will give the same thing. Okay, A is the same matrix. Sorry, A may not be same, because yes, if we take negative sign common, then yes, because then it will be identity. No, because minus of I means yes, so we cannot take that common. So it is not clear that if A is plus identity or minus identity, but from here it is clear that A is diagonalizable. So B is true. So only B is the correct answer. This is true, that is false. Now question number 7, let us see this example. Again, 8 to the power 16 equal to I. From here, immediately we see that if lambda be an eigenvalue of A, then lambda to the power 16 is also 1. Because eigenvalue satisfies the same polynomial equation. Now, minimal polynomial of A can be of degree 2. Can be only of degree 2. This is not correct, right? Why? Why this is not correct? because this also can be a characteristic polynomial or minimal polynomial, or sorry, this can also be a minimal polynomial. So let me write an example which give which will produce the counter example. So let a equal to this thing. So from here it is clear that lambda to the power 16 minus 1. So if we factorize this will be lambda to the power 8 minus 1, lambda to the power plus 8 minus 1 plus 1. Then so lambda 1, lambda to the power 4 minus 1. So this is lambda square minus 1. So lambda 1 plus lambda 1. Then lambda square plus 1. So here we have lambda square, then lambda to the power 4 plus 1. And then lambda to the power 8 plus 1. So all those roots are given by this equation. Equating 0 will get all those roots. Now we need to produce a counter example. Again, we have already constructed. For example, okay, A is 3 by 3 matrix. That is a restriction. So, so let us consider this thing. A to the power 16 must be identity. Okay. Minimal polynomial. The problem will occur because of those kind of things. Here it is algebraic multiplicity of 1 is 1, algebraic multiplicity of minus 1 is 1, but there are also algebraic multiplicity of plus minus I, those are 1, but the problem will occur because of those things. Here the roots may be repeated, is it? No, roots are not repeated. All those roots are distinct. Roots of lambda to the power 4 equal to plus 1 equal to minus 1. What are those roots? Okay, all those roots are distinct, right? Lambda, it divides the circle into 16 pieces, and yes, all those roots are actually distinct. Okay, those will be the roots actually, and all those roots are distinct. So all those roots are distinct, so A must be diagonalizable. So for example, take A equal to the identity matrix. Eigenvalues satisfies this equation, means eigenvalues belongs to the solution of this equation. Okay, eigenvalues belongs to lambda such that lambda to the power 16 minus 1 equal to 0. That is, not all the solutions will give you the eigenvalues, but some of these can give you the eigenvalues. Eigenvalues must belongs to this solution, but they may not. All those solutions may not be eigenvalues. It is clear. It is not possible, because otherwise 3 by 3 matrix that have more than 3 eigenvalues. That is wrong. So eigenvalues are occurring from the solution of lambda to the power 16 equal to 1. Now the first thing, counter example is easy. Here counter example. Here if you take A equal to identity, then clearly what is the minimal polynomial? Minimal polynomial is itself minimal polynomial. It is x minus 1. Identity satisfies this equation. Identity minus identity is 0. So this is minimal polynomial of A. This, it has degree equal to 1. So this is false. minimal polynomial of A can be only of degree 3. Okay, let us check if it is true or not. So A is real matrix. Now the thing is that okay, the problem is that those plus minus I plus minus I is not a thing. That is minus 1 may occur twice, right? Minus 1 or plus 1, those may occur twice. So that may create a problem. Let us see what is the issue with other things. Okay. Oh, sorry, it is already done. Minimal polynomial here we have seen it is of degree 1, so this is wrong. Sorry. There is confusion. Same counter example is working. Now A is either I or A is minus I. Okay, that is actually wrong. For example, A can be, take counter example for C. Counter example for C. Take A equal to this 1 and here plus I minus I. Then it is clear that A to the power 16 will be, because I to the power 16 is 1 minus I to the power 16 is 1. Therefore A to the power 16 from here it is clear that A to the power 16 is I. Oh, but the problem is A is a real matrix. That is also a problematic part, so we cannot use this example. Plus minus I we cannot write here. Okay, but don't. So instead of plus minus I, let us write cos theta, sin theta, minus sin theta, cos theta. This is the block. Now everything is A is real matrix, and here what is the eigenvalue? Eigenvalue it is given by their sum is 2 cos theta. It is 2 cos theta minus 1. And their product is 1. Right. So from here eigenvalues are given by this equation 2 cos square theta minus cos theta equal to 1. But what is the implication of this? Sorry, 2 cos theta minus lambda, and lambda times this is product of eigenvalues is 1. So 2 cos square 2 lambda cos square theta 2 lambda cos theta minus lambda square equal to 1. That is minus 1 equal to 0. From here it is easy to see that what are the eigenvalues. So this is, so plus 1 can be written as okay, is it it is -1. Oh, sorry, it is +1. It is okay. +1. Just a mistake. So +1 can be written as cos square plus sin square. So it is lambda minus cos theta whole square plus sin square theta equal to 0. So lambda equal to cos theta plus minus sin theta. Sorry, plus minus sin theta. Now cos theta plus minus sin theta means we want this to be a root of plus minus I sin theta. Okay. So cos theta plus minus I sin theta means it is e to the power I theta. So this need to be a root of this equation. So is it possible e to the power I theta, e to the power 16 I theta? So this is cos theta. So take any other thing other than so the question is A is okay. Oh, sorry, we don't need to write those kind of things. So it is easier to find a counter example. Just take minus identity here. Sorry about that. Minus identity. Clearly a to the power a square equal to identity. Therefore a to the power 16 is identity. So that is the problem. We need to practice, otherwise easy example we may get trouble with easy example. So sorry, C is false because this is not equal to A is not equal to plus minus I, right? Though it satisfies the equation. There are uncountably many A belongs to R3 which satisfies the above equation. This is also true. This is true. Why?